The topic of of my talk is going to be quantum chaos and entanglement in trap ion crystals. So a little bit of a switching topic again, but hopefully you find some connections to what David was discussing, at least not on the measurement, but at least on the role of entanglement and thermalization. So before I start, I want to, of course, acknowledge the people that did the work that I'm going to present today. This is a collaboration that we have for many years with the Trap Ion group of John Bollinger at NIST, and now Alison is taking the lead, and of course, all the great postdocs and grad students that took the data that I'm going to present, especially Bryce Bullock and my group, my theory group, and Chan Mulady has done a very key job trying to model the experimental data. And of course, a lot of familiar faces that you see here, some people already there that I'm going to briefly highlight what we have been working, like Amit. And well, let's start. So for me, one of the most exciting developments that have happened in the recent years is the synergy that have emerged between different disciplines. So, and I think this is at the heart of ultra quantum matter, because we have people from very different fields. So we have the field of AMO physics, we have condensed matter physics, we have people interested in general relativity, all the way to high energy. And the interesting part is that the joining tissue is the concept of quantum information. And I would say that perhaps one key concept that has been essential for this unification is the idea of scrambling of information, of entanglement. So this is where I think there is some connection with what we heard from David. So just the basic idea that is very common and unique, useful for many different fields, is the idea that even closed systems can thermalize. And so that's the concept of quantum thermalization. And we now understand that there is a one-to-one relationship between thermalization and entanglement of scrambling. And basically, we have a closed system that we can characterize by a density matrix that has tray of rho square equal to 1, that is totally pure. The idea is that we let it evolve, even if we start with a product state and we let the system evolve as a function of time. If the dynamics is non-trivial, then what happens is that we look at a small part of the system, the subsystem A, we trace over the other part, the rest of the system that we call B. And then what we look is that of the purity and the Rayleigh entropy when we take the log of these small subsystems, and we find that's a function of time, that even though we start with a purity that is 1 and therefore a no entanglement and a system with 0 Rayleigh entropy, as a function of time, we see that the Rayleigh entropy grows, the system because loses information in this local system, thermalizes, and therefore we lose track of the information. And when we look at local observables, we see that as the system we're going to a final temperature state. And the idea is that, of course, what is happening is that even though the system is pure, we are losing track of the information that we contain only in the subsystem A. And this is behind the concept of scrambling. So what I'm going to tell you today is a story about scrambling, but I'm going to tell you with a specific system in mind, that is trap ions. So, I mean, I think we all are aware that trap ions has been the leading platform in quantum information in atomic systems. So we have fantastic initial work trying to consider small arrays in 1D RF traps, starting from NIST Boulder, Innsbruck, well, many different institutions, and now they are moving to more scalable systems via a specific QCCD architecture. And you can see companies like Continuum and all these very exciting developments going forward. But in parallel, besides the possibility to just shuffle the ions in a specific region, there has been new developments in the community trying to go beyond the 1D geometries to actually 2D crystals of ions that are much more scalable. And interestingly, this work started many years back here at NIST Boulder, where we have a penning track that has been able to trap between 200 to 300 ions, as I mentioned. But now we see a reviving interest on the community, and not only we have the single penning trap at Boulder, but there are new penny traps that are emerging in Georgia Tech, in Australia. There are micro penny traps that are happening in ETH Zurich, for example, and now the community is moving towards 2D RF traps that also lack of micro motion, and therefore there is an exciting opportunities to actually try to see more scalable systems. And this is why we are interested with, I thought that it's an interesting topic because it's timely. So of course, this talk is going to be focused in the work that we do here at NIST, but scalable and applicable to any other platforms. But because it's the work at NIST, I wanted to start with a short discussion of what is this system specifically. So in this case, we are talking about trap ions of beryllium atoms. And these 2D crystals are formed by using a penning trap. So the penning trap is just a set of stacked electrodes. So you can try to see a cartoon here that introduce the axial confinement of the ions. These are charged particles that introduce an axial confinement. And in order to trap them radially, what the experiment use is a very strong magnetic field and a rotating wall that starts to put the ions to rotate. So the idea is that because of the Lorentz force that a charged particle feels in the presence of a magnetic field, then this Lorentz force generates the necessary radial confinement in order to trap the ions. That, in the addition of the strong color repulsions, then the ions are organized in a triangular crystal. So you can see here the triangular lattices. This is an experimental image, a snapshot of the experiment that is rotating. This is one ion. And what is going to do, we are going to do is that we're isolating two internal levels of the ions that we're going to talk to consider spin down and up. Interestingly, well, you can see that this is happening in a very strong magnetic field. It's the order of 4.5 Tesla, and therefore the energy splitting between these ions between the hyperfine levels are of the order of 100 gigahertz. This is just to give you some numbers, but not some relevant for the details of the talk. So basically, what we wanted to do is we want to use the internal levels of these ions as our degree of freedom that we can control by using microwaves with high level of fidelity. Now, the problem is that in these conditions, the ions are separated in a way that spin-dependent interactions from the column repulsions are too weak. And in order to make the ions talk in a spin-dependent way, what typically the experiments do is to use lasers and use the motion of the ions as a bus, as a mediator to actually generate these interactions. So basically what you can imagine is that there are experiments illuminate or shine lasers on the ions in a way that there are two laser beams that are separated by a common frequency mu. This mu can be seen as imposing a moving lattice on the ions. And with that, what happens is that you can see, because there is a very strong energy splitting of the order of 100 gigahertz, then by controlling the polarization of the lasers and the orientation of the propagation of the lasers that are shined to the ions, what they do is that they can tune them to generate a spin-dependent force. Basically, what happens is that the ions that are in spin up have a force that pushes up, and the ions that are in spin down, these two internal levels, feel a force that's pushed them down. So this term here, SCJ, is the position of the J ion. Sigma C is the Pauli matrix that characterizes the two relevant degrees of freedom, and this mu is the frequency difference between the two beams we call bit node. And we are going to adjust the bit node to actually let the ions talk as we desire. So basically, the important part is that, well, this is a spin-dependent force in addition to the force, to the column repulsion that force the ions to all move as a collective system and not independently. allows to expand the motion of a single ion in terms of the normal modes of the crystal. So basically what we are going to be interested in the modes that are perpendicular to the 2D array. And if you do a plot of these normal modes, these are these pictures of the drumhead modes. For example, I have cartoons of how these drumhead modes behave. And the idea is what we are going to do is that we are going to select the frequency mu to actually, in this case, only excite the center of mass. This is the highest energy mode. The others, you can see that screening of induced by the Coulomb forces reduces the frequency. The center of mass is the high energy mode, and this is what we are going to focus. So we are going to consider the ions all moving all together. So I mean, this is a small, ignore the boundary. I mean, the boundary is irrelevant. So you imagine all the ions moving back and forth together. So under this setting, because this is done by placing the bit node frequency very close to the center of mass node, such that any other excitations become of resonant, then we can write a very simple model. So this the tuning delta is the difference between the bit node frequency mu to the center of mass mode of the frequency of the mode, and then the spin dependent force is just because all the ions are moving together, we replace the C sub I as a daga A, that is the center of mass mode, and because all the ions are heavier, then it's the square root of n. So we have a very simple model where, in addition, because all the ions are feeling exactly the same behavior, then we can ignore what each individual ion is doing and replace this by a collective spin operator. So basically, we are talking of a collective spin talking with the center of mass mode. That is going to be our Hamiltonian for this talk. All right. So now the idea is that, or the questions that we are going to answer is, or try to answer, is how we make this very simple system generate scrambling. And this is going to be done through the Dicke model. I'm going to show you how we are going to implement it. That has been an iconic model that is super simple, but actually show all the requirements that we want to explore: chaos, scrambling, and entanglement. So let's think about what is the Dicke model and how we implement it. Well, the Dicke model is the iconic model of quantum optics. It was introduced in the 50s by Dicke, and is just a large spin talking to an oscillator, a single oscillator, and the only thing that we need to do in our system is to add a transverse field. This is the extra term, because you can see otherwise everything is very trivial, but we add a non-commuting term. So this is the phonons, the transverse field, and then the coupling between the spin and the phonons. So we actually back in 2018, as I'm going to show you, we showed that in the ions we can still implement this model, but let me emphasize that this model has had renewed interest in the coatoms community. So it has been implemented in optical cavities. Lately, it has been also introduced with optical tweezers, but the difference is that, in contrast to optical cavities, where the photons are lossy, in our case, phonons are not. Okay, so now let's try to look a little bit, even just started by the simplest ground state properties of the Dicke model. So the ground state properties, I'm here plotting the energy versus the parameter that is the ratio between what we call this omega divided by a critical value. Just I'm going to explain. What happens is that if you look at the model, there is the ground state features a ground state phase transition at a critical value that is proportional to g squared divided by delta. So in order to understand this, is very simple. I'm going to have, if the coupling g is very small, you can see that you have just phonons and spins, and the ground state is going to be no phonons and the spins pointing along the direction of the transverse field. Very trivial state. This is the ground state in the normal phase, when we have little, basically this g is small. However, or when omega is large. However, when we start to reduce g or decrease omega, so what happens is that below a value of a critical value, then what happens is that we can rewrite, we can complete the square. So this term becomes relevant. You can see that you can recouple field and do a very simple transformation, and now we have a new type of bosonic mode that is displaced. So you have the B is the bosonic mode plus a component that is proportional to SE. So the idea is that you minimize this Hamiltonian, then it's going to be a state that has 0 of the B boson, but that means because the 0 of this B boson means the A boson is highly occupied. So, and moreover, it's going to the ground state is going to be entangled, and it's going to be actually a cut state that is a superposition of the spin up and the phonon displaced along one direction, or a spin down, fully down, and the cut and the phonons displaced along this direction. So this is a fully ferromagnetic state that form a cut state. So in the experiments long time ago, we were trying, or in 2018, we tried to characterize this type of phase diagram. And the idea is that we start by doing very slow quenches. We start by having a very strong transverse field, creating all the spins pointing along the field directions. So this creates the states of the trivial normal phase. And what we wanted to do is to start decreasing the transverse field and see how the system evolved adiabatically into the ground state. We did different type of ramps as we decrease slowly the transverse field. And what we did find is that, in fact, when we look at the magnetization along the Z direction, at very small times, at short times, we do see that depending, well, these are two snapshots depending of the type of ramps that we do at time t equal to 0, because we have 0 magnetization, and then along the Z direction because the spin's pointing along the X direction, so you have a Gaussian distribution. But at the critical point, we see a sudden change in the properties of the magnetization, and you see the two lobes, one along all atoms pointing up, along atoms pointing down. And in fact, that's what we see in the, well, the theory and the experiment agree very well. The only issue is that we have an M-bar initially that was not 0, but 6, and therefore we could not claim anything associated with quantumness in this type of system. So we saw a bifurcation, but it could be also a mix, statistical mixture of the state. So the question is how we can see entanglement in an easier way. So this goes to fast quenches, and that's what we are going to talk about now. So it happens that when you do a quench, you can also characterize a dynamical phase transition. So phase transitions that are characterized, in this case, we are going to look at long time average order parameter that features a non-analytic behavior, and the behavior, this change in behavior can be very well characterized by some changes on the dynamical properties of the state. So this type of phase transitions, for example, has been done in trap ions before. They implemented a pure spin model. This is an experiment that was done in JQI, where they saw a dynamical phase transition between ferromagnetic and paramagnetic phase. We were also seeing a dynamical phase transition in potassium atoms, for example, in a dipole trap, or there have been experiments in cavities with the spinor BECs. So there has been a lot of interest in the community to try to see these dynamical phase transitions in cavities with the related implementation of the Dicke model. They have seen also phase transitions, but in this case, dissipation play a very important role. So the summary here is that even though experiments have seen dynamical phase transitions, they have been caveats. In the case when you have seen quantum behavior, the system is very small. So the universal properties are not so clear when you have such a small system. And the other cases, we see dynamical phase transitions, but those all could be described by a mean field theory. So the question is if we can go beyond that. This is going to be the message of this talk, and this is the experiment that we did. For that, we want to explore the Dicke model. And first, let me tell you what is the dynamical phase diagram. So this, I'm plotting the average magnetization along the Z direction for an initial state that I have, in this case, all the ions pointing along the down, pointing down, the phonons are in vacuum. So I look at the collective time average magnetization along the Z direction, and what you see is that depends on the parameters of the system. I see what is called a trap phase, untrap phase, and something that I call chaotic. So let me explore a little bit what I mean by that. Well, in the case where we can adiabatically eliminate either the spins or the phonons, the system become integrable. For that, what I mean is that imagine that we are in the regime where the tuning of the phonons is significantly large. So it costs a lot of energy to populate the phonons. So in this case, they only mediate the dynamics. They can be adiabatically eliminated. Of course, the position, the X position of the bosons, this is called, I'm going to call this Q in this talk, is going to be a slave to collective magnetization of the spin. And in this case, when I replace this into the Hamiltonian, I have a transfer Ising, Ising model, a collective Ising model with transverse field. This is called the LMG model. And this model has a dynamical phase transition. In this case, it's a factor of 1/2 different to the one of the ground state. It's characterized by a ferromagnetic phase and a paramagnetic phase. Similar, or if I have the other regime where the trapping frequency, the transverse field frequency is much larger, then it costs a lot of energy to flip spins. Instead, I'm going to have the spins a slave to the bosons, and I have a pure bosonic model. And I also see a phase transition. And the very simple way to characterize the phase transition is to go to a mean field picture where I define an order parameter that either can be the collective magnetization along the z direction for the LMG model, or the position X or Q of the phonons, and we can derive a mean field equation of motion and at the end reduce the dynamics of these two order parameters as a dynamic of a classical particle in a potential. So the idea is that depends on the initial energy, then there are two different behaviors. In the case, sorry, I have to reverse the label. Is in this case, the untrapped phase is when the particle can do an excursion across all the potential. It has enough energy to move, or a trap phase where instead the particles can only do a small excursion along as the bottom of the potential. So these are the trap and untrap phase. So this is trap, sorry, and this is untrap phase that we see in the phase diagram. And if you try to look in the Bloch-Sverre picture, the trap phase is that the spins have a very small covering of the tipping angle. They are mostly along the south pole, whereas the untrap phase, they can do excursion across the Bloch sphere. In this case, because the drive is along the x direction, then it's going to be in the cy plane. And similar, because the bosons are a slave to the spins, they are going to do very similar trajectories in the characteristic position and momentum phase space of the phonons. Okay, but we are interested in the chaotic regime that is of course not as simple. And in this case, if we wanted to classify chaos, we start with a mean field treatment of the dynamics when we look at the expectation value of all the different type of degrees of freedom. In this case, the spins and the two variables, the position and momentum variables of the phonons. We can find the equation of motions in phase space, and we can see how much a small change in the initial conditions of in a trajectory is going to lead to deviation of the trajectory. So this x is this collective vector of all these observables, and what we see is the small changes, and if they are characterized by the Lyapunov exponent, if Lyapunov exponent is large, it means that the trajectories are going to exponentially diverge. This is called the butterfly effect. That's very known in classical chaos, and yes, we can see that the system is chaotic in that case. So, and that's we computed the Lyapunov exponent for the Dicke model for this exactly the same plot that I showed you before as the different parameters of the system, and you can see in clear that there is trajectories where the Lyapunov exponent is almost zero. That is what I described before, but there are other regions where the Lyapunov exponent is large, and therefore we see chaotic behavior in this area. So our task is trying to see how we characterize these behaviors in an experiment. So the experiments in this case started not with the phonons completely in the ground state, but there I have two different initial conditions when the mean population M bar is 0.5, so very cold, but not zero, and the other case where the experiment do Doppler cooling, so less cooling, and it has an M bar of 5. In this case, we are operating about 150 ions, and in the other case, the cooler one is about 100 ions. And we're trying to explore this phase diagram that we draw in theory for the initial population with the phonons in the vacuum, and we are going to explore two trajectories. Let's start first the trajectory where we don't see any chaos, where we go between the trap and the untrap phase. So in this case, where we start all the spins along the z direction, in the trap phase, that is for very small values of below the omega critical, we can see clearly that the average magnetization as a function of time is just trap. The ions just keep very close to the south pole, and I start to increase the value of the omega of the transverse field. We can see that the dynamics start to become activated. Here I'm showing trajectories. These trajectory, the dots are the experiment. The solid line are truncated Wigner calculations. These are calculations that include the quantum fluctuations, but also we include all thermal effects or any type of decoherence in the experiment. And the dashed lines that you can see here are mean field calculations. So we can see that in this case, mean field and the truncated Wigner are almost identical. Then we go to actually when we go to the on trap phase, we can see larger excursions as we go up, and then this is where we are going to have more the paramagnetic regime all the way, and we continue making this parameter smaller, and then we're going to go to full paramagnetical type of Rabi flopping. So basically, we do a summary of what expects in the experiments. Instead of looking as a function of time, we look at the average magnetization time of the time average magnetization. We can see very interesting behaviors. First, the behavior of the cold and hot initial conditions are identical to the mean field. That is, so the effect of initial temperature disappears. Moreover, they all agree, so every behavior is very mean field. And this is the ideal behavior when we are able to ignore all the defacing and we can go to to longer times. In the experiment, unfortunately, we cannot. And this is what makes the difference between the sharp transition sinks at the mean field for the ideal case and what we see in the experiment. So notice that this is not any matter of the number of ions, because both of the hot and thermal and cold cases, we have very different number of ions and both agree. So it's because of the long time that we cannot look at in the experiment. Moreover, when we look at the phonons, we can see that, well, there is also not so much difference. The phonons are slaves to the spins in this case, and you can see that there is more phonon population when we have large number of SC because of the slaving. So large phonon population corresponds to large SC, as you see in the trap phase, whereas in the trap there is nothing. So we have characterized our experiment in this LMG code. But let's go and look at the chaotic dynamics. That is what we wanted to see. And we try to see a code in the other direction we can expect to go through chaos. So, well, and the question is how much this is classical, how much this is quantum, and hopefully we can provide an answer. So we start from the left when there is no chaos to the right. So first, we are going to see initially the trap trajectory as we expect from the LNG dynamics, and we plot a phase space dynamics of the expectation value of SY and SC. This is experimental data, and you can see kind of a periodic orbit, not so bad. But as we enter into the deep chaotic regime, we are going to start seeing first mean field is different from the truncated Wigner and the experiment. Second, temperature matters. The hotter case dumps faster, and you can see the emergence of chaos in phase space. You can see erratic trajectories. This is cool because this is experimental data. You can see the particles go in one direction and then it's kick up and continue another orbit. And then as we go deeper in the other phonon-dominated regime, we start to see periodic orbits, still mean field, and truncated Wigner disagree. And when we go even deeper in the phonon-dominating regime, we can see more periodic behaviors. So a summary of this data is given here in this plot. So you can see A, B, C, D are shown here as A, B, C, D. So here we are going to go in the trap regime. This is the average magnetization as a function of time between omega divided by delta. And we can see that, well, we have a disagreement between mean field and the experiment and the truncated Wigner approximation. We see, moreover, that in this average observable, hot and cold are very similar, but clearly, I mean, we can see that expectation of C goes to 0 in the chaotic regime, and very interesting sharp behavior in this case. But if you now, well, we can also plot on the theory, this is not measuring the experiment, the phonons, and we can see that the phonons in the chaotic regime are macroscopically populated as expected. But not so much difference, just more phonons in the hot than in the cold as expected. But the question is quantumness. Can we say that the system is quantum here? Well, not so much. We can see discrepancies, but the question is we can have a genuine measurement of quantumness in a chaotic system. So that's what it led us to start with a different initial state. Instead of starting all the atoms pointing along the z direction, now we are going to start the atoms pointing along the x direction, where if I have no initial photons populated, if they start in the vacuum, there is no mean field dynamics. So instead, we have to do truncated Wigner calculations, and this is the truncated Wigner calculations. I'm showing now the average expectation value of the magnetization as x. Of course, it will zero if there is only mean field. So the fact that you see dynamics, everything is beyond mean field. And this is the calculated Lyapunov exponent between different parameters. This is for 100 particles, and I'm going to focus here in the dynamics when omega is equal to delta. This is very important, and we're going to say, and these are some samples of the truncated Wigner, and we are going to see along these different crosses of the phase diagram. Interestingly, we can see that in this point where the G is small, we can see that the expectation value of C doesn't thermalizes, it goes to a finite value, or it thermalizes but not to zero, whereas I go deeper in the chaotic regime, it goes to zero very quickly. And moreover, well, even though the Lyapunov exponent is larger here, clearly here we see more chaos. So we wanted to distinguish between instability and chaos. And this is where we are started to do, I mean, these are a little bit more truncated Wigner calculations for different number of atoms. We can see from 100 to 1 million, and we can see, in fact, in the regime that is not chaotic, we see difference. I mean, we see that the average Lyapunov exponent start to vanish here, and is not vanished in the other regime. So then the question is how we're going to characterize this type of dynamics. And well, let me go back to a very simple case. Then this is what we are going to focus in the experiment. We are going to focus in the regime first, where imagine delta and omega are large. And then we are going to work in the regime where G, the coupling, is small. And we are going to start here exploring what we expect in the dynamics. So we can go to the rotating, we are going to go to the rotating frame set by this trivial single particle Hamiltonian. And when we do that, then both the phonons and the spins are going to start to rotate, one with frequency delta and the other with frequency omega. But clearly, if you multiply these two terms, and now we write SC as an effective S plus S minus along the X direction, I mean, because that's the direction where the spins are pointing out, we can see that when delta is equal to minus omega, then all the other terms are rotated out, and the dominant terms are a term that is a daga S plus along the direction of the X direction. So this term, interestingly, what it's telling me is that I start with all the spins along the X direction. As a function of time, I'm going to start with an spin flip along the X direction and an excitation in the boson. Then after I have another excitation in the boson and another spin flip. So basically, the state of the system is just going to be a correlated state where the n number of excitations grow equally to the number of spins that I'm flipping. So this is kind of a thermophile double state. It's a very correlated state. And we can see that from the dynamics, there is exponential growth in the excitations. So this is equivalent if we go to flan land line. So basically, if we are going to start going into the regime where we are going to start to generate a bosonic excitations, you can start seeing that actually these excitations, we treat them as a boson, are generated in pairs. And this is analogous to the case of two-mode squeezing, holography, well, double field thermal state. This can be used in APR states. And basically, you can understand this as an unstable fixed point where you are going to have a lot of excitation, and moreover, we're going to have a squeeze quadrature, two squeeze quadratures. And I see that I'm running out of time, so I'm just going to mention that this state is going to be very similar to what people talk about EPR states, because there is correlation between the spins and the two quadratures of the bosons. But basically, to go to the punching line, even though, I mean, I just want to say this state is very key for a continuous variable teleportations that we are going to hopefully do soon in the ions. But just to finalize, you can see that this is experimental observable. So we go for the regime where we expect to have chaos, omega equal to delta, and we see exponential growth of correlations, but very quick saturation of the magnetization in not agreeing with the mean field. And as we go to regimes where we have a more closer to the pair production regime, we see exponential growth, but we see some oscillations. And then in the regime where we start the two-mode squeezing, jumping, that we see the system becomes integrable, but we see these revivals that are really generated by entanglement. So I think we clearly see the emergence of quantum chaos. We in this plot, we can see that if we attribute the growth of this agreement because of thermal effects, you can see that any addition of thermal nodes in our system is not able to capture the correct dynamics. So showing that we indeed have quantum chaos in our system, in the sense that the system is chaotic, but still features unique thermal behavior. And well, I mean, we can also characterize some type of squeezing in our system that come up in the integral regime. But just let me finalize by saying that we believe that this type of chaos and scrambling can be a very useful resource for actual bidirectional teleportation. I don't have time to explain a little bit, but we think that there is a strategy to use the Dicke model for both hidden prescale recovery protocols and teleportation in the same setting. So I don't have time, but Amit is there, and hopefully he can provide some information about this. And let me just finalize in that, saying that even though I told you exciting behaviors in 2D crystals, now the experiment is moving to more three-dimensional crystals where we are going to have very exciting dynamics. And with that, thank you. I'm sorry for running out of time.
So we're running a little late, but we'll take a couple of quick questions. Too much pressure on the audience. Okay, if not, let's take on Maria again and move on with the program. Thank you.